how to balance chemical equations. So before getting into balancing chemical equations, just want you to know that the side on the left, so there's kind of a left side and a right side, kind of that's separated from this arrow. The stuff on the left side are going to be called your reactants. The reactants. The stuff on the right side is just going to be called your products, okay? Now, when you're trying to balance a chemical equation, you want to make sure that the stuff on the left side, the elements or, just the elements, compounds, whatever, on the left side is the same as, the amount of elements on the other side. For example, if I have, let's say, 2 white atoms, and let's say I have 2 shaded white atoms, okay? So I have 2 of these atoms and 2 shaded atoms. When these react with each other, I should get the same amount of atoms. You can see 2 of the same amount of atoms right now. So the type of atom on each side of the reaction has to be the same, and the amount of the atom has to be the same. I will just repeat that again. The type of atoms has to be the same, and the amount of atoms has to be the same. And this is going to be called the law of conservation of mass. So during a chemical reaction, you can't just randomly spawn another atom out of nowhere. The amount of stuff on one side just has to be the same as the amount of stuff on the other side. And when you're trying to balance a chemical equation, all they're trying to ask you is, how can you make the amount of atoms in this equation the same on both sides? And let's get into it. So what I like to do is I like to write kind of a chart, okay? So right now, we have 1 zinc atom, okay? So we have 1 zinc atom on the left side. We have 1 hydrogen atom on the left side. And we have 1 chlorine atom on... what did I write 2? Okay. 1 chlorine atom on this side. On the other side, we have 1 zinc atom. We have 2 hydrogen atoms now. So on the other side, we have 2 hydrogen atoms. On the other side, we have 2 hydrogen atoms, so you can see it's uneven. And we also have 2 chlorine atoms. This is also uneven. So how can we balance this? Whenever you're balancing a chemical equation, all you're worrying about is the coefficients. So I'm talking about the stuff in front of your molecule or atom. Never ever change the subscripts of the atom. Okay, never ever, like, let's say if I was trying to balance this and I change this hydrogen into a 4, you can't do that, okay? You have to change the amount of it by using the coefficients, not by, changing the subscripts, okay? So that's a really important thing that y'all need to know, okay? So we're only going to be putting stuff in these 4 areas. Now, how can we balance this? Well, let's try to balance the hydrogens first. So right now, we have 1 hydrogen, and the other side has 2 hydrogens. So what we're going to do is put a 2 here. 2 times 1, you can think about this as a subscript of 1. That's just going to be 2. So our new amount of hydrogen is going to be 2. And don't forget, you have to distribute the 2. So now there's 2 chlorine atoms. So don't forget to make sure you distribute the 2. And when you look at that, the stuff on both sides are the same. Therefore, this chemical equation is balanced. And if your teacher wants to, just put 1s on the place that you didn't write any subscripts. But, either way, I think it's fine. N2. No, let's say this reacts with hydrogen gas. Nitrogen gas reacts with hydrogen gas, and this is going to yield ammonia. So this is a synthesis reaction. This is also going to be in the video, but just kind of just throwing that out there. And let's write down our chart again. So we have 2 nitrogen atoms, 2 hydrogen atoms, 1 nitrogen atom, and 3 hydrogen atoms on the other side. 3 hydrogen atoms. How can we balance this? You can see that the amount of nitrogen on this side, well, that's different. So what we're going to do is multiply this by 2. Multiplying this side by 2, well, you can think about this as distributive property. You're distributing the 2 to the nitrogen so that this 1 becomes a 2, and 2 times 3, this 2 times 3, that's just going to be 6. Well, because we did the distributive property, now our hydrogens are messed up even more. So how can we balance this? Well, since we have a total of 6 hydrogen atoms on this side, we take the 6 and we divide it by this subscript. 6 divided by 2 is going to be 3. And now we can see that 3 times 2, that's 6. So now we have the same amount of atoms on each side. So our final balanced equation is just going to be N2 plus 3H2. It's going to yield 2NH3. And you can put a 1 here as well. And that's going to be our answer. We have iron. This reacts with oxygen gas to yield 2, 3. Okay. Let's make our little chart again. Fe, there's 1 of it. O2, this is 2 of it. Fe2, that means there's 2 irons. O3, well, there's 3 oxygens. Usually you want to start out balancing your metals. So we're going to balance our iron first. Well, we see that we have two irons on this side. So we're going to put a 2 here. So now our amount of iron, that's going to be 2. How do we balance the oxygen, though? Well, the common denominator, you can think about it, if you were to have like 2 and 1 over 2 and 1 over 3, your common denominator is going to be 6. So on this side, we're going to multiply this side by 3. And this side, we're going to multiply this side by 2. So that now our amount of oxygen atoms are the same. So the amount of oxygen atoms are going to be the same after we do this. But now, you can see that, yes, we have 6 oxygen atoms, because 3 times 2, that's 6. And on this side, 2 times 3, that's also 6. But now the problem is that 2 times 2, that's going to be 4. So that means that, once again, we're going to have to change this iron, the amount of iron, to 4. And that's going to be our answer. So our final equation is going to be 4Fe plus 3O2. This is going to yield 2Fe2O3. So I think in the context of this problem, it would have been better, or it would have been a little bit faster to balance out the oxygen atoms first. But either way, even if you balance out the other element first, you're still going to get the same result. So it's it's going to be fine. Either method works. Sometimes you just want to choose the faster method, then you would balance out the oxygen. Let's say we have 2 Na, or let's say we have Na and 3. It's gonna plus N2. And, you know, this is going to be a decomposition reaction. You know, and later we're gonna talk about those. So just a heads up. And creating our little chart. 1 Na, 3 nitrogen, 1 Na, 2 nitrogen. So we have a 3. We have a case where we have a 3 and a 2 again. So how can we make this equal? Once again, you know, going back to what I was doing last time, if we have 1 over 3 and 1 over 2, to get a common denominator, we would multiply this side by 2 and this side by 3, so that now we get a common denominator of 6, which is what we're going to do. On this side, we're going to multiply by 2, because 2 times 3 is 6. On this side, we're going to multiply the nitrogen by 3. 3 times 2 is 6 also. So now our nitrogens are going to be balanced. But now, the problem is, once again, this 2 here has to be distributed to the nitrogen and the sodium. So our sodium is going to be 2. Which means that this sodium has to have a coefficient of 2. And now we can see everything is balanced. So this is going to be our final. Say we have CH4 plus O2. It's going to be carbon dioxide and water. And this is going to be a combustion reaction because it reacts with, but, you know, once again, that's another heads up for what we're going to be learning later. And let's create this chart. So we have 1 carbon. We have 4 hydrogens. 2 oxygens. And we have 1 carbon here. We have 2 hydrogens. And we have, looks like we have 3 oxygens. I don't know why I wrote it different ways this time, but, you know. So normally, you know, when you're dealing with carbon, hydrogen, and oxygen, so these type of reactions involving these elements, what you want to do is you want to balance your carbon first, then your hydrogen, then your oxygen, okay? So first, second, third. These are going to be your steps to balancing it. First, let's balance out the carbons. And it looks like, well, our carbons are already balanced. Let's move on to the hydrogens. Balancing our hydrogens, well, we will just put a 2 here. 2 times 2 is 4. So there's going to be 4 hydrogens now, which means that this is balanced. But wait, this 2 not only multiplies to the hydrogen, but also to the oxygen. So now, our oxygen, well, we already have 2 here. 2 plus 2, because there's this invisible 1 here. 2 plus 2 is going to be 4. So now there's going to be 4 oxygen atoms. And in order to balance those 4 oxygen atoms, well, you would need a 2 here. 2 times 2 is 4. So now we have 4 oxygen atoms. And our thing is balanced. We have 1 carbon, 1 hydrogen, and 1 oxygen. So remember, carbon, then hydrogen, then oxygen. Because if we were to balance out the oxygen first, well, it would be pretty tricky because there's 2 things with oxygens in them. So, you know, to make it simple, we'd balance out, you know, the stuff in this order. Okay, so now we would have 1 sodium, 2 chlorines, 1 sodium, 2 chlorines. Or no, 1 chlorine, sorry. 1 chlorine. How would we balance this? We want 2 chlorines. We want 2 chlorines on this side. So we're going to put a subscript. We're not going to change the subscript. We're going to put a coefficient of 2 here. And this 2 is going to distribute so that now the amount of chlorines we have is 2, but also the amount of sodiums, that's going to be 2. So we would have to put a 2 here in front of the sodium. And yeah, iron, CO2, Cu, FeCl3. Let's make our table. CO2, then Fe1, Cu1, and then Cl is going to be 3. How would we do this? Well, we ought to balance out our chlorine atoms first. So once again, it's a situation where we have this 2 and a 3. And you already know what we got to do. Put a 3 here, put a 2 here. 3 times 2, that's 6. 2 times 3, that's 6. So now our Cl atoms are going to be balanced. They're going to be 6. But now, let's look at all the other changes we done. 3 times this 1 right here. 3 times this 1. That's going to be 3. So we're going to have 3 Cu atoms. Now, 2 times 1, this invisible 1 once again. Well, that's going to be 2. So how would we balance this now? Well, luckily these are these single elements, so we can adjust this pretty easily. So on the Cu side, because we have 3 on the left side, we would put a 3 on this side so that this would be balanced. And because there's a 2 iron atoms on this side and only 1 on this side, we put a 2 here, and now this would be balanced. So it would be 2Fe plus 3Cu, Cl2, the Cu's. This is going to yield 3Cu plus 2FeCl3, and that is this is going to be added to H2O to yield H3PO4. This one's a bit tricky, so I'm just going to write the table once again. So 4 phosphorus atoms, 10 oxygen atoms, or 10 plus 1, my bad. Remember this one right here, so 11 actually. And then we have 2 hydrogens. And then this is going to produce 3 hydrogens, so hydrogen 3, 1 phosphorus, 4 hydrogens, or sorry, 4 oxygens. This one's a little bit tricky, so how would we balance this one? Well, once again, we want to balance our metals, and we can see that on the right side, you know, metals ain't that balanced. So we put a 4 here so that now our metals are balanced. But remember, distribute. Now 4 times 3, that's going to be 12 hydrogen atoms. 4 times 4, that's just going to be 16. So we're going to have 16 here. Now, how would we solve this? Well, in order to balance out the hydrogens, we have to multiply this one by 6. So now, 6 times 1, that's just going to be 6. And we know that 6 plus this 10, that's going to give us 16 oxygen atoms. And we know that 6 times 2, that's going to give us 12. How convenient. So now everything looks balanced. And, you know, there's our final answer. Okay. Right now we have 3 carbon atoms, 8 hydrogen atoms, and 2 oxygen atoms. On the right hand side we have 1 carbon atom. We have 2 plus 1, that's going to be 3 oxygen atoms. And we have 1 hydrogen atom. how can we, or 2 hydrogen atoms, my bad. Did it wrong. 2 hydrogen atoms. So how can we balance this? Remember, carbon first, hydrogen second, oxygen third. Let's go. So right now, we have to multiply 3 on here so that our carbons are balanced, you see? Now our carbons are balanced. But then this changes the amount of oxygen. 3 times 2, that's just going to be 6. So now we have to balance our hydrogens. In this case, 8 on this side divided by 2 on this side gives us the coefficient of 4. So now we have 8 hydrogens. But the problem is that now, while distributing this, we have 4 oxygens. So now distributing this 4, we have 4 oxygens plus our 3 times 2, which is just 6. So now we have 10 oxygen atoms. So now at the end, we would just put a 5 here, because 10 divided by 2 is 5. And it looks like everything. Say that this one's pretty tricky. Okay. And we're gonna have 6 carbons. We're gonna have 14 hydrogens. We're gonna have 2 oxygens. On the right hand side, we're gonna have 1 carbon. We're gonna have 2 hydrogens. And we're gonna have 3 oxygens. How can we balance this? Remember, carbon first. We're gonna put a 3 there. My bad. How can we do this? Well, we can put a 6 here. So that now, 6 times this invisible 1, that's going to give us 6 carbon atoms. But remember, we have to distribute to this oxygen. So now we're going to have 12. This is going to be 12, right? Plus this 1 right here. Plus this 1 oxygen atom there. And that is going to give us 13 oxygen atoms. Now we want to balance out the hydrogens. So now we know that this 14 in total divided by this 2 gives us the coefficient of 7. So we are going to put 7 here. 14 here. Put the coefficient 7 there. And when distributing this oxygen, we get 12, right? Plus 7, that's going to give us 19. So now we have 19 oxygen atoms. So now what we can do to balance out the oxygen is we can divide this 19 by the 2 so that we get this 19 over 2 oxygen atoms. Yes, this equation, or let me just, 19 over 2. Okay, yes, this equation is balanced, okay? Just 19, because these 2's kind of, you can think about them as canceling out. So this equation is balanced. But the problem is that we want whole numbers. So how can we get a whole number? Well, we would just multiply this equation by 2. So that now these 2's would cancel out. And the rest of the 2's get distributed all the way through. So when the 2's cancel out, 2 times this, which is just 2C6H14, plus, wow, 19O2, because the 2's cancel out. This is going to give us 2 times 12, that's 12CO2, and plus 2 times 7, that's going to be 14H2O. So let's check if our answer is correct. So right now we have 2 times 6. 12 carbon atoms. And yes, indeed, we have 12 carbon atoms. 2 times 14, 28 hydrogen atoms. Well, guess what? 14 times 2, 28 hydrogen atoms. 12 times 2, that's 24. 24 plus 12. 14 times 1, that's going to be 14, or 38 oxygen atoms. And well, guess what? 19 times 2, that's also 38 oxygen atoms. So this is our final balanced equation. Whenever you get a fraction, make sure to multiply your equation by some number to get rid of the fraction. We do not want fractions in our chemical equations, okay? So whenever you have like an odd number, let's say 13 divided by 2, well, you know, you're going to have to multiply the whole equation. I'm talking about the whole thing by 2, okay? Everything, every unit by 2 to get your final answer. Finally, we have this equation we need to balance. So whenever you're dealing with a polyatomic ion, right? So PO4 is this a polyatomic ion. And whenever you have two of the same polyatomics on one side, on both sides, you should treat it like a unit. So what I mean by that is I'm going to make PO4 equal to X. So now our new equation is going to be this H3X and then K3X plus H2O. And then now we can balance it. So first, we can see that if we make this table, and then oxygen, it's going to be 1, and we're going to have 4 hydrogens, and then 1 X, and we're going to have 3 potassiums here, we're going to have 2 hydrogens, and we're going to have 1 oxygen, and 1 X. Now we can balance. So let's put a 3 here because our metals aren't balanced. So when we put a 3 here, the K distributes to the O, so 1 times 3 is 3, and distributes to the hydrogen. 3 times 1 is 3, plus this 3 right here, that's going to be equal to 6. So we're going to have 6 hydrogens now. Now, in order to balance out the hydrogens, well, take a look at here. 6 divided by 2 is going to be 3. So now this 3 is going to distribute to this hydrogen, that's 6, and to the oxygen. Oh, and to the oxygen, which is going to give us 3 O's. And would you look at that? This is now balanced. So our final equation, if we were to write it with the polyatomic here, is going to be 3KOH plus H3 of this PO4. It's going to produce K3 plus K3X. I forgot to PO4. And then plus 3H2O. And that is going to be our final balanced equation. So whenever you have the same polyatomics on both sides, just treat it like how you would treat an atom, okay? Just like a single thing. You don't have to write out every element inside the polyatomic ion. First, we're going to talk about the types of chemical reactions now. So the first type is going to be called synthesis reactions. So an example of a synthesis reaction is 2Na plus CO2 gives us 2NaCl. When you think of synthesis, you might think about building up. So you have these 2 units, and when they react, they combine to this one bigger unit. In this case, these 2 units, they build up to become this one bigger unit. Let me show you another example. 2Li plus Br2 this is going to give us 2LiBr. And once again, you have this one part that's combining with the other part to give us this one bigger part. Okay, so that's just synthesis. Next one, we're gonna have decomposition. Okay, decomposition. Basically, the opposite of synthesis. So when you have, let's see, let me just give you the opposite of this, 2NaCl, you know, when this thing decomposes, well, this is going to give us 2Na plus Cl2. So when you have this bigger unit, let's call it AB, this is going to be broken down to its components, aka A plus B. Just the opposite of synthesis reactions. There are two types of decomposition reactions: electrolytic type reactions and thermal reactions. And based on the name, you can kind of predict, you know how these reactions kind of are. One involves electricity and the other one involves heat. So let's talk about the first one. This is when you just, use electricity to kind of fuel your reaction. So let's say if we have 2H2O, well, this is going to decompose by means of this to 2H2 plus, or don't say plus, but and O2. So one involves electricity and the other one involves heat. So when I mean heat, I don't mean like placing something directly under the flame. So say that we have this like glass tube, okay? We place our thing in there and we place a flame underneath. There's like this flame underneath it, but we're not placing the thing directly underneath. Say this was like a Cheeto or something we're placing in to burn. Well, we wouldn't be placing the Cheeto directly underneath the flame. We would be placing it in a glass tube, exposing it to heat so that this reaction would occur. So that's what I mean by thermal decomposition. And an example of this would be, let's say we have CaCO3, and this will undergo decomposition to get CaO and CO2. And the way you would kind of express that a reaction is a thermal type decomposition reaction is on top of this arrow, you would have this little triangle sign. This indicates that your reaction is thermal decomp, okay? Thermal decomposition, okay? Just write decomp for short. So this little triangle thing, make sure to write it whenever, there's a thermal decomposition reaction. For the first type, you don't have to write anything, okay? This is exactly what it sounds like. One element replaces another element in a compound. So say that we have an ionic compound. Say that we have element A. This is a cation, positive ion. And this is going to react with BC. Obviously, when you're naming ionic compounds, cation's first, anion is second. When this reacts, the A is going to replace the B, so it's going to be A, C, and then plus B. So this A just took the spot of B, just switched places. And, that's all the single replacement is. So if we have 2 iron plus 3 CuCl, this is going to make 3 Cu. See, this iron knocked this Cu atom out of its place, and instead the Fe atom teams up with the Cl. So the cation and the anion teams up. So you're going to get 2FeCl3. Now, there's a really important thing to know about these types of reactions. So, okay, this is called the activity series, okay? And there's more to this, but basically, elements like at the top. So, I'm going to draw like 2 arrows here, okay? And then here. So, elements that go from here, they have the highest activity level. And you go down here, and then you go down here. Elements here, they have the lowest activity level. Okay? So the elements here, I'm sorry I couldn't fit all the elements in one line. Usually these elements and these elements would be in one line. So, the highest to lowest would look, it would look a bit more organized. But I'm sorry about that. But you'll see, once again, that if we go back to our reaction, okay, 2Fe plus 3CuCl, 2, this one. So 3Cu plus 2FeCl3. The reason why the Fe atom can swap places with the Cu atom is because its spot on this activity series is higher than the Cu spot on the activity series. Do you see? So the Fe atom is on a higher position than on a Cu metal. So you would say that because the Fe atom, this is more active than the Cu atom, it is able to react. And, it would be able to do the single replacement reaction. If the tables were turned and the Cu atom, if you have like 2 Cu, and this reacts with, I'm just making this up, this isn't actually a thing, but like this, where the stuff was swapped, well, you would say that this would be no reaction. Why? Because the Cu atom is not active enough to knock out this Fe atom. So in order to swap positions with another atom, you have to be higher on the activity series. So you can think about this as, I don't know, which atom is stronger. If the atom is stronger, it's able to knock out, aka the atom's higher on the activity series. If the atom's weaker than the other atom, it's not able to knock out the other atom. Therefore, there would be no reaction. Now let's talk about double replacement reactions. But first, let me just talk about some other stuff about chemical equations. So in a chemical equation, you might see something. I haven't written them out yet, but now I'm just going to show you. So you might see these little things at the bottom, right? So let me just write out, like, this isn't a double replacement reaction, but let me just write out this. You might see these little symbols on these chemical equations. And what these symbols mean is it's just a state of matter. So kind of S, this represents solid. L represents liquid. G represents gas. And AQ or aqueous, this just means that thing is dissolved. This thing is dissolved in water. Okay. So these are just little like symbol things that you should keep in mind, because from now on, especially in the double replacement type reactions, those symbols are going to be really important. Example of a double replacement action where you have these two parts. Let's call them A, B, plus let's call them these two parts C, D. This will form, well, this will be a positive ion, this negative, positive, negative. This two parts will group together, and these two parts will group together. You have to write it like CB because the cations always go first when you're writing these types of equations. But you see how the cation kind of pairs with the anion in the other section, and then the cation pairs and then pairs to the anion on the other section. And this is the case for this one. This one pairs with NO3. The Cl pairs with the Ag. And you can see right now these two things have swapped. And these two things have swapped right now. So there are two types of double replacement reactions. And this is one example of a precipitation reaction. So let me just write that. So, okay, precipitation, and I forgot to write this. This is aqueous, okay. So remember those like little symbols, I was referring to? Well, a precipitation reaction is when you have, two aqueous, right? This is a double replacement. And when you get your result, you get one aqueous and one solid, okay? So when these two things react with each other and the double replacement thing happens, when you get an aqueous and when you get a solid, that reaction is a precipitation reaction. So let me give you another example. Na2SO4 plus BaCl2. So react, and these will be aqueous. And when they react, this will be 2NaCl aqueous, and then you'll get BaSO4 aqueous. And you'll get BaS. So now you can see that we started off two aqueous, right? And when these two react, we get one aqueous and one solid. So that is just a precipitation reaction. You get one solid and one aqueous from the reaction. Now, how would you know that a reaction is aqueous? How do you know that you're going to end up with a solid? Well, this is why, I'm just going to pull up my reference guide. Well, just tells you which kind of combinations, which compounds are going to be aqueous and which compounds are going to be solids. The stuff in this row, right? The group, that's inside the arrow. So this group right here, this is going to be aqueous, okay? So if you see anything that involves this, you know that it's going to be aqueous, okay? So every one of this, you can pause the video to check everything, but all of this group down is going to be aqueous, except, and then you can see the exceptions. When something is combined with these compounds, then it's actually going to be a solid. So if I just write it down here, this column means that if something's in this column, it's going to be aqueous. If something's in this column, this is going to be solid. If something is in this column, however, this is actually going to be a solid because it's insoluble. And this is going to be aqueous. So you can pause the video. I'm just going to slowly scroll through. And whenever you're dealing with a double replacement reaction and you want to know if it precipitates, you look at this table. So remember, let's go to the first reaction actually. So remember the part that, we said it was solid, the AgCl? Well, if we didn't know that it was solid, well, let's check. And we can also check this one, the CaNO3, to see if it's aqueous or not. Back to our thing. So our aqueous thing is going to be NO3, right? Well, guess what? NO3, which is nitrate. Well, guess what? This is indeed going to be aqueous because it's in NO3. And if we check, let's see, or the AgCl right here. Look, halides, remember AgCl, this is normally going to be aqueous, but the exception says that except when paired with Ag. So therefore, this is going to be, once again, a solid. This is going to be a solid, which means that we are right. Now let's check this other reaction. Let's see if this NaCl, well, I mean, it's so obvious, you know. So, oh, would you look at that? Group 1 ions, they form soluble compounds, aka aqueous. So the NaCl part was correct because there are no exceptions to this. And if we look at the BaSO4, well, let's just scroll down. Let's go down one by one. SO4. SO4. I think we reached it. Sulfates are going to be aqueous, except when they're paired with Ba. Remember the BaSO4 we were talking about? This thing is a solid. You see, this is in the exceptions list, which means that this is going to be a solid. Another type of reaction, another type of double replacement reaction is called an acid-base reaction. And this is when our first thing, AB, reacts with the acid. So your CD is going to be an acid. And in order to know if it's an acid, we must go to the acid table. Of all these acids, and if your kind of second part, fits in with one of these acids, well, it's going to be an acid-base reaction. And when there's acid-base reaction, you're going to get a salt, which is your ionic compound. So it doesn't have to be the literal NaCl salt. It can just be any ionic compound. And there's your water, H2O. So this is just the second type of double replacement reaction. And I just wanted to do one more thing. Just want to explain one more thing. So if we have aqueous and then we have another aqueous, and when this reacts, it makes two aqueous. So we have two aqueous, Bi2. So this is supposed to be a solid, right? But if this were to be a aqueous, this reaction would not occur, okay? So when you combine these two aqueous compounds, into this double replacement reaction, if your reaction, you end up getting two aqueous as the result, there is no reaction, okay? Just take note of that. So a combustion reaction, this is the final type of reactions we're going to be talking about. This is when you're burning something with oxygen. So one of your reactants is always going to be oxygen. And when this reacts, you're usually, sometimes you're reacting a metal with oxygen and you're going to get a metal oxide. And, sometimes you're reacting a hydrocarbon, and when this reacts, you're going to get CO2 and H2O, or water. And because this is a plus energy, we know that this reaction is exothermic, meaning that it releases energy, okay? So another example of this combustion reaction, remember, we talked about burning hydrocarbons. So this will yield 3CO2. So once again, when you're burning a hydrocarbon, and this reacts with oxygen, once again, you're going to get CO2 gas and you're going to get H2O, or water. And also remember what I said about the metal oxide thing. This combustion reaction doesn't have to always happen with hydrocarbons. It can happen with metals as well. Let's see another example. This combustion of iron, so Fe, and then this reacts with O2 to form Fe2O3, your metal. And when reacted with oxygen, this is going to give you your metal oxide, okay? So this is obviously a little bit different from this part where you have your hydrocarbon. And this forms carbon dioxide and water. And yeah, that's pretty much it about doing this chemical equations.